So we're going to close out Chapter 8 with applying the concept of confidence interval to means and how we would estimate a mean using a confidence interval based off of a sample mean. So instead of having, like we had in the last section, p hat plus or minus a z star times the standard error. Okay. And again, the calculator does all that heavy lifting for us. Now we're estimating a mean, so we use x bar. And as we saw already, we're using a t-distribution, t star, and this standard deviation is probably actually a little bit simpler than that for proportion. So first thing we want here in this section is just to find t star. How do I know how many standard errors I should add and subtract to have a certain level of confidence? So what I would like here is 90% confidence and my sample size is 10. So if my sample size is 10, that means I have degrees freedom 9. Okay, so I'm going to go to my table of values. This is probably the quickest way to get it, but we can also use our calculator for this, and I'll show you how that works. So for 90% confidence, if we go all the way down to that t-distribution, and here it is, okay, you'll see that 90% confidence, we can find it down at the bottom very easily if we're not sure at any point. So here's 90% confidence. It's the fifth column in. And 90% confidence will have 5% in each tail. So that's another way we can identify it. If we come up to the top, we should have 5% in the tail. And since we have 9 degrees of freedom, that's a critical value of 1.833. So t star would equal 1.833. We'll tag a plus or minus in front of that. So what does this look like on the calculator? So remember, if we wanted to use second vars and our inverse t, number 4 here, we can do that. But remember, what's in the tail? 0.05. Is the area in the tail, and we had 9 degrees freedom in this situation, and we should get the same value, negative 1.833. Again, I have 1.833 because your table value is always going to give you the right tail, but it's a plus or minus, right? We have plus, we're adding and subtracting that many standard errors. Okay, so for part B, we are going to have to use the calculator, right? If I want 99% confidence and I have 95 observations, that means I have 94 degrees freedom, and you're going to see on your chart that's not there. There is no 94 degrees freedom, so we'd have to use a conservative estimate, or we would just use our calculator in this situation. So I'm just going to hit second enter. It's a little shortcut. So if I have 99% in the interval, then the area to the left would be 0.995, right? We have 5%, like half a percentage in that interval, and we have 94 degrees of freedom here. So we put in comma 94. So that's the only extra thing you have to tell the calculator. With inverse norm, the mean and standard deviation are always 0 and 1. For a t-distribution, the standard deviation is always changing. So we have 94 degrees freedom. We have to tell the calculator how many degrees freedom we have so it knows the specific standard deviation. So I get 2.629 for that t star. All right, now since the t-distribution, since our distributions for means get more normal as sample size gets larger, we have to be careful when we have a small sample size. So what we want to look at in this next example is to determine if the t-distribution is appropriate when we have a really small sample. So determine whether we can safely use a t-star critical value. Well, since I only have a sample of 5, right, n is small. So since n equals 5 is small, and there appears to be an outlier, then the t-distribution is not safe in this situation. We can't safely assume normality. So the t procedures would not be ideal there. And to be honest with you, in practice, and I've done research and published a thesis, we would still use it. We would just put those notes in our research. For sure, you're not going to just stop and say, well, maybe you try to get a bigger sample. That would solve your problem, but generally, you're still going to publish your work if you can. So here I have a sample size of 100. So even though there's outliers here, it doesn't matter, right? We can assume normality, and we can use t star. So remember, with the t-distribution, we're assuming an approximate level of normality since n equals 100. And remember, as long as n is 30 or more, that's usually a pretty safe assumption. So this one, I'm going to have to jump to the next page of the notes. But a middle school counselor wants to estimate how many minutes on average students spend doing homework. Histogram of amount of time doing homework previous evening for a random sample of 20 students is shown below. So we definitely want to look at this histogram because it's only 20 students. It's not 30 or more. So here the histogram looks roughly symmetric and mound shaped, no evidence of outliers. So it seems like the t-distribution would be safe here in this situation, since the distribution of 20 times looks to be mound-shaped and symmetric. Remember, the samples usually represent, they resemble the population that they're pulled from. So we can be safe with that. So we're going to do two things here. Ann and Tori want to estimate the average weight of an Oreo cookie and see if it's less than advertised. Right? Oreo advertises that their cookies are 3 cookies are 34 grams. So if we take 34 and divide it by 3, that's what 1 cookie ought to weigh. They get an X bar of 11.39, which I would imagine is a little bit less than what they're advertised to weigh. So we want to know, like, even though this is less than what they might be advertised to weigh, is it significantly so, right? And we take a sample of 36 cookies. So we're going to use a confidence interval to do that. So if we find that we have a confidence interval that the advertised average weight does not live in, if the whole interval lives below what they advertise, then we would be 95% confident that they're not as big as they're advertised to be. So when I see this construct and interpret 95% confidence interval, remember what I like to do there. I want to go to my confidence interval template. Okay, so the parameter of interest now, instead of this being p, is going to be mu equals the true mean or true average weight of an Oreo cookie. Okay. The formula for the standard deviation of the sampling distribution, again, this is easier now. It's the standard deviation, the sample standard deviation divided by the square root of n. In this case, it would be square root of 36. Conditions for valid inference. We would like to see that they took a simple random sample. So let's double back and see if it tells us that. It says that for their project, they selected a random sample. Okay, so when I see that in the text, I'm going to make note of that. Okay, I'm going to put in quotes random sample. Okay, I put it in quotes because that means it's stated. And so it takes away any kind of like assumption on my part. I can say they told me they took a random sample. Okay, I want to have a normal sampling distribution. And we know this is good because they took a sample of 36. So we say n equals 36. So that condition is satisfied by the central limit theorem, right? CLT. And then finally, we want the observations to be independent. Our rule of thumb for that is they're independent, right? 36 is less than 1/10 of all Oreos in the population, okay? There's certainly more than 360 Oreos out there in the population. All right, so our calculation and our interpretation, how does this flesh out? Well, the sample mean was 11.3921. So I have 11.3921 plus or minus, I need a t-star value for 35 degrees of freedom, right? So I don't think I'll be able to find that on my table. So I'm just going to go ahead and use inverse t. So second, I'll just cheat here and do second enter. And this is a 95% confidence interval, so this is going to be 0.975. And we have 36 cookies, so that's 35 degrees of freedom. Okay, let me just double check that it was 95% confidence. Yeah, I thought I saw that. Okay, so my t-star is going to be 2.03. So it's going to be plus or minus 2.03 times my standard error estimate, which we go back is 0.0817. That's the sample standard deviation, 0.0817. But remember, that's for the sample, so we have to divide that by the square root of 36, which is just 6. Okay? So I fill into the formula, but I'm going to let the calculator do the heavy lifting here. Okay? We're going to go to Stat and to Tests. If you have a NSPIRE, you're going to go to right to your confidence intervals. You're going to go to Menu and find Statistics and Confidence Intervals. So what we have here is just a very simple T interval. Anytime you see T interval, we're assuming we're using T for means. Okay, and that's the mantra that we want. Second mantra we had variance is always add. The second tattoo I got in college when I graduated was that we always use T for means. So remember that if we're estimating means, whether it's a hypothesis test or whether it's a confidence interval, we'll always use the T interval, okay, or T distribution. So I do have the stats. I don't have data. If I had a list of numbers, I would select data here. So I have to tell the calculator that the sample mean was 11.3921. Okay. Then I have to tell the calculator what the sample standard deviation was, and that was 0.0817. Make sure you use the sample standard deviation. Okay. And our sample size was 36. You don't put degrees freedom there, you put in the actual sample size. And then this would be 0.95. Okay. So if I were to calculate that out, I get 11.364. Okay. All the way up to 11.42. So that's my confidence interval. And then we articulate it the same way we always have. We are 95% confident that mu is in this interval. And I already said what mu was up here, so I don't have to restate it. I'm giving my interpretation in context. So let's remember what that interval is, or I'll bring it back up on the next screen because that's going to be key to it. So part A, I answered all on my template. Okay. Part B, does it provide convincing evidence that the cookies are smaller than advertised? So 3 cookies are supposed to weigh 34 grams. So 34 divided by 3 would tell us that they should be about 11.33 grams per cookie. All right, so let's write that down. They're advertised as 11.33 grams each. Okay, I got that from what they said here. So when I go back and I look at my interval, 11.33 lives below the interval, right? So since the 95% confidence interval is entirely above 11.33, so the company contends that they're 11.33 grams each. We have a 95% confidence interval that lives entirely above that. So we actually are 95% confident that mu is bigger than 11.33 grams. Okay, that's how I would draw a conclusion from that confidence interval.